I welcome you all for the week 7 live interactive session for the course Polymers, Concepts, Properties, Uses, and Sustainability. Now let's get on to the session. Let me share my screen. So let's have a brief recap of lectures of week 7. So week 7 lectures were based on viscoelasticity in polymers. So, lecture 45 was on viscoelasticity and introduction. This was a concept based lecture. So, an introduction to what is a viscous response, elastic response, and its molecular view, and what happens in case of macromolecules. So, what is a viscoelastic response? What are the contributions? And then the definition of Deborah number, and what is a terminal response? And you know what is elastic, viscous, and viscoelastic response is a matter of time. So these things were discussed, and then polymer sample subjected to creep and recovery. So how does the response change? Basically, this was discussed using an example problem from gate. Next, lecture 46 was on thermal response. Again, this was a conceptual lecture. So, here, high temperature response for different polymers. What are the thermal signatures in a polymeric systems? And then there was a brief discussion on annealing process. And then there was a discussion on DSC, differential scanning calorimetry, TGA, and TMA. And then there was a little in-depth discussion on the DSC response of polymers, and how does the thermal conductivity of polymer, is, there was a discussion on thermal conductivity of polymers. Uh, okay, so these were all discussed in the thermal response of the polymers lecture. Next, in lecture 47, this was again on viscoelasticity characterization. So, this was a concept based lecture. So, how do you quantitatively measure the viscoelasticity? What are the static tests? And how do you do the dynamic test? So, first of all, you should have some certain theories, and then you set some geometry, and then you have some type of experiments, and then you try to correlate the theory with the experiment so that you understand how the structure is based on this dynamic testing. And then the type of deformation were discussed, and how the sample geometry is decided, and what are the control variables, what are the measured variables were discussed. And then there was a discussion on creep and stress relaxation. Lecture 48 was on viscoelasticity. This lecture was on simple models. This was again a concept based lecture. And when is viscoelasticity important? And what is the relaxation process? What is a linear viscoelasticity? And then void model and Maxwell model. These two models were discussed in this lecture, where in void model, a free response was discussed, and in case of Maxwell model, the stress relaxation response was discussed in detail. Lecture 49 was on dynamic mechanical analysis. So, this was a property based lecture. So, oscillatory testing, and there was a discussion on Maxwell model and its response for oscillatory testing. And then uh, there was a detailed discussion on DMA. So, different sample geometries with different fixtures. How is rate and frequency important? And then stress or strain control, temperature control in DMA. So, these were discussed. And then the region of viscoelasticity, especially there was a discussion on your storage and loss modulus. And the next lecture, lecture 50, was on damping application. It was a uses based lecture. So, here, first of all, energy dissipation during a stress strain cycle. So, here it was, a discussion on energy dissipation, which is nothing but the product of stress with strain rate. And then the expression for the energy dissipation was arrived. And then energy storage during stress and strain cycle, which is nothing but the product of stress and strain. So this was discussed. And then damping of vibration and sound absorption was discussed. And how is the viscoelastic response of polymer was discussed in detail. Viscoelastic response of rubber was discussed in detail. And viscoelastic response of rubber was also discussed based on the standard linear solid model. And then there was a discussion on damping materials with examples. Lecture 51 was on time temperature superposition. So this was a properties based lecture. So first the discussion started with linear viscoelasticity. What is the integral statement of the Maxwell model? And then the Boltzmann superposition principle was discussed, and viscoelasticity in polymer and its temperature effects, and what is time frequency temperature equivalence, and shifting of data measured at different temperatures for obtaining this time temperature superposition. Okay, based on shift factors and other parameters were discussed. Lecture 52, which was the last lecture of this week, was on impact and energy absorption. It was a uses based lecture. So, what is a high rate of loading, and what is energy and stress intensity? So, this was all based on the impact uh, and failure process, energy under stress strain curve, fracture energy, stress intensity factors. So, these aspects were discussed, and then there was a discussion on the polycarbonate ABS blends and alloys. And then certain trade tests on impact strength measurements. Basically, the ISOD and Charpy tests were discussed. And then values for these ISOD and Charpy tests for different polymers were also shown in this lecture. Now, let's get on to the practice assignment session. First question. The behavior of a polymer is described by Maxwell model consisting of a spring element of modulus 10 power 10 Pascal in series with a dashpot of viscosity 10 power 12 Pascal. In the solid, 50 seconds after the sudden application of fixed strain of 1%, the stress will be dash into 10 power 7 Pascal. So, this is a GATE 2021 question. So, what have they given that the So, what are the parameters that are given in the question? So, they've given that the polymer behavior follows Maxwell model. So, Maxwell model is you have a spring and dashpot in series. Spring is this one, which is having a modulus E, and the value of the element of modulus, spring element of modulus is given as 10 power 10 Pascal, and dashpot element viscosity is given as 10 power 12 Pascal seconds. Now, what is the Maxwell model? So, Maxwell model expression is given by sigma, which is nothing but stress, plus lambda, which is nothing but your relaxation modulus, dou sigma by dou t is equal to eta max into E dot. E dot is nothing but your strain rate. So, they've given that the modulus of the spring element is 10 power 10 Pascal. Well, viscosity of the dashboard is 10 power 12 Pascal seconds. And the time they have given, is 50 seconds. So, the strain is applied for 50 seconds. Okay. So, initially, so they've asked what is the stress. So, time is 50 seconds and your strain is 1%. So, 1% means your strain is 1 by 100, that is equal to 0.01. Now, what is the stress relaxation response? Okay, so a constant strain is applied. Okay, and now they have asked the stress, and the strain has been applied for. The stresses are the amount of stress in the system after 50 seconds of the fixed strain application. Sudden strain application is what is asked. So you have the expression for the Maxwell model. Sigma of t is equal to E max into E naught into exponential of minus t by tau. So your tau, sorry, T by lambda minus T by lambda. Your lambda can be calculated as lambda is equal to eta by Emax. So you have the value of eta as well as Emax. So it is 10 power 12 by 10 power 10, that is nothing but 100 seconds. And they have asked what is the stress uh, what is the stress after 50 seconds of the strain application. So sigma of t, so here t is 50 seconds, so sigma at 50 seconds is given by, you have the Emax value which is nothing but 10 power 10, E naught which is nothing but your constant strain which is 1%, that is equal to 0.01, so it is 0.01, and your time t is given 50 seconds, and you have calculated lambda which is nothing but 100. So you just have to substitute in the expression for the stress. Mhm. So sigma at 50 seconds is equal to 10 power 10 into 0.01 into exponential of minus 50 by 100, that is equal to 6.06 into 10 power 7 pascals. This is what is the solution for this problem. Next, question number 2. Match the following changes observed in the calorimetric analysis of a polymer sample when heat flow is plotted against temperature. So heat flow is plotted against temperature. So basically this is, the changes in a that has been done during a differential in a differential scanning calorimeter. Okay. So what are the changes given, and what are the uh, corresponding phenomena that is happening to that particular change. So first, PQR. So P is step increase in heat flow, Q is exothermic peak, R is endothermic peak. So what are the process? So crystallization, melting, and glass transition. So this is again a GATE 2014 question. Now we have to match which of these changes corresponds to which of these phenomena. So what does a step increase in heat flow indicate? The step increase in heat flow indicate glass transition. Exothermic peak indicates crystallization process, and endothermic peak indicates melting. So this is how generally your DSC curve looks like. So heat flow versus temperature. So there's a step change which indicates the glass transition process, and then your uh, exothermic peak which indicates the crystallization process, and your endothermic peak basically indicates your melting process. Stress relaxation equation for polymers is given by sigma is equal to sigma naught into exponential of minus T by tau, where sigma is the stress at any time instant t, sigma naught is the initial stress, tau is the relaxation time. The relaxation process is temperature dependent and follows the Arrhenius law. For a rubber sample, the relaxation time is 60 days at 25 degrees centigrade. If the above, so part 1 question is, if the above sample is stressed to 2 megapascal initially, then the time required to relax the stress to 1 megapascal will it be 31.6 days, or will it be 41.6 days, or will it be 51.6 days, or will it be 61.6 days? Second part of the question is, if the activation energy for the relaxation is 30 kilojoule per mole, the relaxation time at 35 degree centigrade will it be 30.5 days, or will it be 35.5 days, or will it be 40.5 days, or will it be 45.5 days? So this is a GATE 2012 question. So how to solve this problem? So what is given? First of all, we have given the expression for the stress relaxation. So sigma is equal to sigma naught into exponential of minus T by tau, where sigma is your stress at any time, sigma naught is the initial stress, tau is the relaxation time, and Next is they have given that the initial stress is 2 megapascal. That is what is given in the part 1 question. The sample is stressed to 2 megapascal initially. That means sigma naught is 2 megapascal. Then the time required to relax the stress to 1 megapascal. So the final stress is 1 megapascal. And they have given stress relaxation experiment. That means it's a constant strain is applied. So the stress decreases with the time. Okay. So they have also given the relaxation time is 60 days at 25 degrees centigrade. So now, if you check the above expression, we have what is stress, final stress that is reached, that is to 1 megapascal, and initial stress is 2 megapascal. They have given the relaxation time also 60 days. Now we have to calculate the time required for the stress to fall from 2 megapascal to 1 megapascal for a constant strain of a stress relaxation experiment. So we have all the parameters. So sigma is 1, sigma naught is 2. So 1 is equal to 2 into exponential of minus t by 60, where 60 is your relaxation time. So we have all other parameters. So you will get the time required for the stress to fall from 2 megapascal to 1 megapascal is 41.6 days, which is nothing but your option B. Next, part 2 of the question. So they have said that the relaxation process is a temperature dependent and follows Arrhenius law. So what does this says? That the relaxation process is temperature dependent. That is fine. It follows Arrhenius law. That means the relaxation process follows Arrhenius temperature dependence when it is away from its glass transition temperature. When it is closer to glass transition temperature, it follows the WLF equation. Okay. So it is away from the uh, glass transition. Okay. So Arrhenius law for relaxation process. So the relaxation time lambda is given by lambda is equal to e power EA by RT. Where EA is your activation energy, R is universal gas constant, and T is temperature. Now, we have certain information. We know that for 25 degrees centigrade, your relaxation time is 60 days. They have asked what will be the relaxation time if the temperature is increased to 35 degrees centigrade. Okay. And they were, so we know R is 8.314 joule per mole Kelvin. And they have also given the activation energy, which is 30 kilojoule per mole. So, which is nothing but 30 into 10 power 3 joule per mole. Now, what we have to find out? We have to find out the relaxation time for 35 degree centigrade or 35 degrees Celsius. So, now we have to convert all to, your SI units. So, temperature will be 25 degrees centigrade means it is 298 Kelvin. So, 35 degrees centigrade 308 Kelvin. So lambda 2 by lambda 1 is, we have the expression for lambda, which is nothing but lambda is equal to e power EA by RT. So lambda 1 will be e power EA by RT1, and lambda 2 will be e power EA by RT2. Okay, so just dividing lambda 2 by lambda 1, we will get lambda 2 by lambda 1 is equal to exponential of EA by R into 1 by T2 minus 1 by T1. So here again we have all the other parameters except the relaxation time at 35 degrees centigrade. So lambda 2 by 60 is equal to exponential of 30,000 by 8.314 into 1 by 308 minus 1 by 298. So if you do the math, you will get your lambda 2 is 40.5 days. So which is nothing but your option C. So if the temperature increased from 25 to 35 degrees centigrade, the relaxation time reduced from 60 days to 40.5 days. Okay. Now next, notched impact strength of plastic decreases with, does it decrease with increase in notch tip radius, or increase in notch depth, or increase in temperature, or decrease in notch depth? So, uh, how does the notched impact strength of plastic decreases with? So this is again a GATE 2015 question. So notch is nothing but, so you have something like this. You could see in the figure. This is, some kind of an opening. This kind of opening is called as a notch. This opening, in a continuous element is called as a notch. Okay. So notched impact strength of a plastic decreases with increase in notch depth. If this notch depth increases, the impact strength starts decreasing. Okay. Next question. Deborah number is the ratio of dash, and when Deborah number is very much smaller than 1, then the relaxation process would lead to dash. So there are two questions in question number 5. First is, what is Deborah number? Deborah number is ratio of something. Okay. So what is that ratio? And then when the value of Deborah number is very much smaller than 1, then the relaxation process would lead to what? So the Deborah number is nothing but the ratio of relaxation time to the experimental time. Okay. And when Deborah number is very much less than 1, so we know that it's a ratio of relaxation time to experimental time. So Deborah number DE is equal to lambda by T. So that means when Deborah number is very much less than 1, that means lambda by T experiment is very much less than 1. That means either lambda tends to 0, either the numerator tends to 0, or your denominator experimental time tends to infinity. That means when numerator tends to 0, when the relaxation time tends to 0, that means there is an instantaneous relaxation. That means there's a quick dissipation of energy. So when Deborah number is very much less than 1, the relaxation process would lead to dissipation of energy. Or when your experimental time scale is large enough, that means the material has sufficient time to relax completely and dissipate energy. So in this way also you say that when Deborah number is very much less than 1, there is a dissipation of energy. Okay, the process would lead to more dissipation of energy. Next, creep refers to application of dash. What does the creep experiment refer to? What do you apply in a creep experiment? So, in a creep experiment, a constant stress is applied. Okay, and you find out what is the strain as a function of time. Next, dash refers to use of thermal energy for rearrangement of molecules or crystalline phase, blend domains, and copolymer domains in polymers. So, what is the process where they use thermal energy for rearrangement of molecules, or rearrangement of a crystalline phase, or rearrangement of a blends domains, or rearrangement of copolymer domains in polymers? So this process is called as annealing. Annealing is a process where they use thermal energy for rearrangement of molecules. Okay, so the material is taken above the glass transition temperature, and then the rearrangement of molecules or crystalline phase or blends, blend domains, and then copolymer domains are brought in. Next, formed polymers have dash thermal conductivity than normal polymers. So does it have higher thermal conductivity, or does it have lower thermal conductivity, or does it have a very similar thermal conductivity, or none of the, it doesn't have any relation, none of the above is the right option. Polymers in general have lower thermal conductivity. Okay, now what about the case of foamed polymers? So when we come to the case of formed polymers, the formed polymers will have much lower thermal conductivity than the normal polymers, because polymers as such they have lower thermal conductivity. We could see that the value of thermal conductivity for polymers is zero point 0.1 to zero point 0.6 watt per meter Kelvin. So when it comes to formed polymers, again between the polymer chains there are empty spaces, or kind of bubbles or empty spaces. So basically a foam kind of a structure. So that means there is again an air gap between the polymer molecules. That means further the thermal conductivity is reduced. And you could see the value of the thermal conductivity of formed polymers to be 0.01 to 0.08 watt per meter Kelvin. That means there is a one order reduction when it comes from when it goes from a normal polymer to a formed polymer. Okay. So there is a the formed polymers have lower thermal conductivity than normal polymers. Next, Hookean solids has dash compliance and relaxation has dash compliance and relaxation modulus for viscous or Newtonian fluid is. So Hookean solids they have a constant compliance. Okay, whereas the relaxation modulus for viscous or Newtonian fluid is 0. How? So the concept of your compliance comes for a creep response. So creep response is nothing but a constant stress is being applied. Okay. So constant stress is being applied. Your compliance is given by the ratio of strain as a function of time to constant stress. So when it comes to a Hookean solid, we know that for a Hookean solid, for a constant stress applied, the strain is also a constant. That means the strain is also not going to vary with time. And the expression for compliance is nothing but strain as a function of time by constant stress. So here the strain is also going to be constant. That means a constant value divided by constant strain by constant stress. So that gives your compliance for a Hookean solid to be constant. Okay. And what is a relaxation modulus for a Newtonian fluid? So Newtonian fluid relaxation modulus. So a relaxation modulus is given by stress as a function of time by constant strain. Okay. So in case of a Newtonian fluid, there's an instantaneous stress decay. Okay. That means they are able to uh, you know uh, uh, once the strain is applied, the stress falls to uh, 0. To maintain the strain, you do not need the stress to be maintained. It immediately falls to 0, because once you apply a constant strain, then uh, uh, the fluid changes its structure and goes to a state which is completely changed. Okay. So and that changed state or that deformed state cannot come back, so there is no requirement for a stress to be maintained to maintain that deformed state. So that means your relaxation modulus for a viscous or Newtonian fluid is 0. Okay. Because your relaxation modulus is given by stress as a function of time by constant strain. Okay. And for a Newtonian fluid, since there is an instantaneous stress decay, your relaxation modulus is 0. Next, according to Maxwell model, for oscillatory response, as the frequency increases, dash response dominates, while dash dominates at lower frequency. What kind of response dominates as a frequency increase, and what kind of response dominates at lower frequency for a Maxwell model under oscillatory testing? As the frequency increases, there is a elastic response that dominates, because the material does not relax, and it's more in a frozen state, so your elastic response dominates. And at lower frequencies, the material is having ample amount of time to relax, so your viscous response dominates. So this is how your curve looks like. So at as the frequency increases at higher frequencies, the material, it moves to a more of a elastic dominant state. And at lower frequencies, you could see that your E double prime dominates over the E prime. So that means your viscous response dominates. So material is having sufficient amount of time to relax for the segmental flexibilities and other relaxation process to happen. So your viscous response dominates. Next, 1 by eta into E dot the whole square is energy dash during the stress strain cycle. Is it the energy absorbed or energy dissipated during the stress strain cycle? Half eta into E dot square. Eta is your viscosity, E dot is your strain rate. So, uh, this expression is actually the energy dissipated during a stress strain cycle. So, this was discussed during the energy dissipation discussion during the stress strain process. Okay, when the damping, this was on lecture of damping application. Okay, so if you actually rewrite this expression of half eta into E dot square, so this was basically for a Newtonian fluid. It is nothing but half eta into E dot is nothing but your sigma, your stress, and your E naught dot is nothing but your strain rate. So stress into strain rate, you will get your energy dissipation per unit time, per unit volume. Next, damping behavior increases with strong secondary interaction. Identify if the statement is true or false. Does damping behavior increases with secondary interaction? Because in damping behavior, the material should dissipate energy. So damping behavior is basically a measure of how much energy you are able to dissipate over how much energy you are able to store. So if the secondary interactions are higher, will the material be able to dissipate energy, or will the material not be able to dissipate energy? So it's actually damping behavior increases with strong secondary interaction is false. Okay. Damping behavior generally decreases with strong secondary interactions and crystallinity. So if the secondary interactions, for example, in case of cellulose and all, you have a lot of hydrogen bondings and all. So the ability to dissipate the energy is lower. So the material cannot dissipate energy so easily. And similarly in crystallinity also, in crystalline phases, the ability for energy to dissipate, because the crystalline phases, you have more of your energy storage. Okay, that is why your crystals, in case of your metals and all, where your crystallinity levels are all higher, there is more of a elastic dominant behavior. So the material cannot dissipate energy that easily. That means your damping behavior is lower in these cases. So it decreases with strong secondary interactions and crystallinity in the material. Next. In thermorheologically simple materials, temperature affects all relaxation modes identically, and time temperature superposition can be carried out in these systems. Is it true or false? I repeat the statement. In thermorheologically simple materials, temperature affects all relaxation modes identically and time temperature superpositions can be carried out. Is it true or false? It's actually true. So, in thermorheologically simple materials, the temperature effects of all relaxation modes are identical, and this makes the time temperature superposition possible in these materials. But if the material is having some kind of crystalline phase or anything, then the changes in relaxation modes are different. So that will be thermorheological complex materials, and doing the time temperature superposition in those systems will be difficult. So for time temperature superposition to be possible, the material should be thermorheologically simple, where the relaxation modes or all temperature affect no temperature affects or temperature effects on all relaxation modes are identical. Okay, ISO test is based on per unit dash of crack. Is it based on per unit area or per unit length or per unit volume of crack? So ISO test is basically for impact strength testing. So basically your ISO test is based on per unit length of the crack. Whereas in case of Charpy test, it is based on per unit area of the crack. Next, question number 15. From the dynamic mechanical analysis of a polymer sample with a phase angle of 30 degree, the relation between storage and loss modulus can be expressed as dash. This is a GATE 2022 question. Can it be expressed as E prime is equal to square root of 3 into E double prime? Or is it 2 times E prime is equal to square root of 3 into E double prime? Or is it E double prime is equal to square root of 3 into E prime? Or is it D 2 times of E double prime is equal to square root of E prime? Which of these is the right answer? So they have given DMA for a polymer sample has been done, and the phase angle they have given as 30 degree, and they have asked for relation between your E prime and E double prime. So how do you solve this problem? First of all, given the phase angle delta is equal to 30 degree. So tan delta, it gives a relationship between your storage and loss modulus. So tan delta is nothing but your loss modulus divided by storage modulus. So tan delta is equal to E double prime by E prime. So we know what is the value of delta. Delta is 30 degree, which is given. So tan 30 is equal to E double prime by E prime. So if you know the value of tan 30, we know what is the relation between the E double prime and E prime. So tan 30 is nothing but 1 by root 3. So 1 by root 3 is equal to E double prime by E prime. So your E prime is equal to root 3 into E double prime. So which is nothing but your option A. So the relation between your storage and loss modulus when when phase angle is 30 degrees is uh, E prime is equal to square root of 3 into E double prime. Next, question number 16. A 3 millimeter thick layer of softened PMMA at 190 degree is sandwiched between two flat parallel plates. A shear stress of 100 kilopascal is applied to the softened polymer. Assuming the softened polymer is a Newtonian fluid with an apparent viscosity of 3.9 into 10 power 4 pascal second, the relative sliding velocity between the two plates is dash. So they have given PMMA at 190 degree having a thickness of 3 mm. It's a softened PMMA. Is sandwiched between two parallel plates. So a shear stress of 100 kilopascal is applied to the softened polymer. Okay, they have also given the apparent viscosity. Now they have asked what is the sliding velocity. They've also given an assumption that the softened polymer can be assumed as a Newtonian fluid. So how to go about this problem? So PMMA at 190 degree between two flat parallel plates. Thickness of PMMA y is equal to 3 mm they have given. Applied shear stress tau is equal to 100 kilopascal. Apparent viscosity eta is equal to 3.9 into 10 power 4 Pascal seconds. So now assuming PMMA as a Newtonian fluid. That means Newton's law of viscosity can be applied for this system. So Newton's law of viscosity is given by shear stress is equal to your viscosity into du by dy, where du is your change in velocity by dy is nothing but your length. So change in length. That is nothing but your strain rate. Your stress is proportional to strain rate, where the proportionality constant is your viscosity. So we have the value of stress, which is 100 into 10 power 3 Pascal. We also have the value of eta, which is 3.9 into 10 power 4 Pascal seconds. We do not know what is the relative velocity, but we know the thickness, which is 3 millimeter, that is 3 into 10 power minus 3 meter. So, including all the values in the expression and then rewriting the expression, you get your du is equal to 100 into 10 power 3 into 3 into 10 power minus 3 by 3.9 into 10 power 4. So you will end up with your you will end up with your relative viscosity, relative velocity between the two plates as 0.0076 meter per second, which is nothing but 7.692 millimeter per second. Because they've asked the value of sliding velocity, relative sliding velocity in millimeter per second. So we are just converting from meter per second to millimeter per second. This is nothing but 7.692 millimeter per second. Next. Damping factor of a solid polymer under sinusoidal loading in a single cantilever mode showing 80% recovery in modulus is. So this is a GATE 2015 question. So they have asked for damping factor of a solid polymer. They have given that the loading is sinusoidal, and they also have given that 80% recovery in the modulus. Now, how do we find the damping factor? So your damping factor is nothing but your tan delta. So damping factor is equal to tan delta. So tan delta is nothing but your loss modulus to storage modulus. It is the ratio of loss modulus to storage modulus. Next, they have given 80% recovery in modulus. That means the storage modulus is 80% because 80% is recovered. That means 80% is stored back. So storage modulus is 80%. So the remaining 20% is lost. That is why it is loss modulus, right? Whatever is lost is loss modulus, and whatever that is recovered or stored is the storage modulus. So storage is 80% and loss is 20%. So damping factor can be is equal to tan delta, which is equal to loss modulus by storage modulus, which is nothing but 0.2 by 0.8, that is equal to 0.25. So this is how you find the damping factor. Next, the impact strength of polystyrene can be enhanced by blending or mixing with. Can it be improved by blending with carbon black, PMMA, polybutadiene, or glass fiber? How can you increase the impact strength of polystyrene? This is again a GATE question. This is asked in GATE 2018. So the answer is C. So the impact strength of polystyrene can be enhanced by blending or mixing with polybutadiene, which is nothing but a synthetic rubber. So rubber can be used for improving the impact strength. Mhm. And also as a damping material. So in those two applications, they are used, you know, very well. Okay, next. Strain gamma in a polymer melt varies with time on application of stress S by the following relation. So the relation is eta into d gamma by dt plus g into gamma is equal to S. So if a if a steady shear stress S naught is applied, then strain at steady state gamma naught is given by, how do you know express gamma naught for a polymer having the following relationship when a steady shear stress is applied. So the relationship is given by eta into d gamma by dt plus g into gamma is equal to S, where S is your stress and gamma is your strain. They have also given a steady shear stress of S naught is applied. So they have asked what is the steady state gamma naught. So is it S naught by G, or is it S naught by eta, or is it S naught into G, or is it S naught into eta? So what is the steady state gamma naught? So the answer is, so first of all, they have given steady shear stress is S naught. Next, what is the strain at steady state? So at steady state, your change in strain with respect to time is 0. So d gamma by dt is equal to 0. That means this entire first term in this expression goes off. So that means your gamma naught is nothing but your S naught into G. Because if your entire first term goes off, it will be G into gamma naught is equal to S naught. So your gamma naught is equal to S naught by G. So it is option A. So we have to note down that the point that it is at steady state. Steady state, d gamma by dt is equal to 0. That is how you arrive at the answer for this question. For a viscoelastic material behaving as a Maxwell model, the modulus at its relaxation time under constant strain reduces to, does it reduce to 36.8% of its initial value, or does it reduce to 63.2% of its initial value, or does it reduce to 66.7% of its initial value, or does it decrease to 33.3% of its initial value? So this is again a GATE question, GATE 2008 question. So what have they given? They have given a viscoelastic material, and this material follows Maxwell model. So they have asked, uh, you know, the modulus at its relaxation time. The value of modulus at its relaxation time under constant strain. Okay. So your Maxwell model expression is sigma of t is equal to sigma naught into exponential of minus t by tau. Here they have given that they've asked for modulus at its relaxation time. That means t is nothing but your relaxation time. So t is equal to lambda. Okay. So sigma of t is equal to sigma naught into exponential of t minus t by lambda, that is lambda by lambda, which is nothing but 1. Okay. So sigma of t is equal to 0.368 into sigma naught. So that means 36.8 into sigma naught. Right? That means your modulus reduces by 36.8% of its initial value. Okay, which is nothing but your option A. Next, this is the GATE 2024 question. The linear viscoelastic behavior of a polymer is described by the Kelvin-White model, consisting of a spring element of elastic modulus 10 megapascal in parallel with the dashpot of viscosity 3.6 into 10 power 11 Pascal seconds. A fixed stress of 40 megapascal is suddenly applied to the polymer and maintained thereafter. The value of strain after 1 hour from the sudden application of stress is dash. So what they have given? They have given a polymer. They've also given the polymer is going to have a linear viscoelastic behavior, which can be described by a Kelvin-Voigt model. They've given the spring elements elastic modulus is 10 megapascal and the dashpot viscosity is 3.6 into 10 power 11 Pascal. They have given a constant stress or a fixed stress of 40 megapascal is supplied. That means it's a creep experiment. They have asked the strain after 1 hour of sudden stress application. Okay, a fixed stress or constant stress of 40 megapascal is applied and it is maintained. That means it's a creep experiment, a constant stress experiment. And we have to find out the strain as a function of time, and they have asked the strain after 1 hour. So first of all, viscoelastic behavior of polymer follows Kelvin-Voigt model. In Kelvin-Voigt model, you have a spring element in parallel to dashpot element. And the elastic modulus of spring element they have given as 10 megapascal, which is 10 into 10 power 6 pascals. And then viscosity of dashpot eta they have given as 3.6 into 10 power 11 Pascal seconds. They have also given fixed stress sigma naught is equal to 40 megapascal, that is 40 into 10 power 6 Pascal. Now Kelvin-Voigt model is given by E of t is equal to sigma naught by E into 1 minus exponential of minus t by tau r, where E is your strain at time t, sigma naught is your constant stress, E is your elastic modulus of spring element, 1 minus exponential of minus t by tau. T is actual time and tau r is your retardation time. So now your retardation time can be obtained by the ratio of your viscosity of dashpot divided by the modulus of the spring element. So eta by E. So eta is 3.6 into 10 power 11 and E is 10 into 10 power 6 pascals. So 3.6 into 10 power 11 by 10 into 10 power 6. So this will give you your retardation time as 3.6 into 10 power 4 seconds. That is nothing but your the value is 36,000 seconds. Now they have asked strain after 1 hour of stress application. So E of t that is equal to E of 1 hour that is equal to E of 3,600 seconds. E at 3,600 seconds. So t is equal to 1 hour that is equal to 3,600 seconds. So you just have all other parameters in this expression of strain at t. So strain at 3,600 is given by sigma naught by E into 1 minus exponential of minus t by tau r. So E of E at 3,600 seconds is equal to 40 into 10 power 6 by 10 into 10 power 6 multiplied by 1 minus exponential of minus 3,600 by 36,000. So that is nothing but 4 into 1 minus exponential of minus 0.1. So 4 into 1 minus 0.9048. So your strain at 3,600 seconds is 0.3808. So strain after 1 hour of stress application is 0.3808. Was the result. Next, there were certain questions posted in one of the earlier sessions forum. So these were all the questions on how do we solve questions 16, 22 and 24 in assignment 6. So this was the question. So they've given figures where they've given dielectric loss for a pure polymer polyvinyl methyl ether PVMe in figure A, and in figure B they have given for blend of PVMe with polystyrene. So question 16 was this variation of dielectric loss in the frequency range of 1 to 10 power 6 hertz indicates the following phenomena. Does it indicate interfacial polarization, or does it indicate molecular polarization, or does it indicate electronic polarization, or does it indicate or does it indicate atomic phenomena? So the answer is actually molecular polarization. This is a direct question from the lecture. So your dielectric spectroscopy, it is in the range of 10 power minus 3 to 10 power 6 hertz. So which is basically your molecular relaxation process or molecular polarization process. It is associated with translation, rotation and vibration modes of bonds and molecules, which gives the mechanical and dielectric response of the material. Okay, next. Relaxation time for the rightmost curve in figure B will be of the following order in seconds. Will it be 10 power minus 5, or will it be 10 power 5, or will it be 10 power 1, or will it be 10 power minus 1? So this is the figure B. Though, so the rightmost curve peak is at the frequency of, so the peak of the rightmost curve, if you can look at my pointer, you could see that the peak of the rightmost curve is at a frequency of 5. So they have also given it is a uh, uh, graph of log of frequency versus your uh, epsilon double prime. Okay. So your frequency is uh, log of nu is equal to 5. That means your nu is, you're taking log to the other side, it will be 10 power 5 hertz. That means 10 power 5 second inverse. So your omega lambda is equal to 1. So your lambda is your relaxation time, where omega is your angular frequency. So so your relaxation time and your angular frequency are inversely related. And your frequency and angular frequency is related by nu is equal to 2 pi omega. So if your nu is going to be of the order of 10 power 5 second inverse, then your time, your relaxation time will be inverse of it. So it will be 1 by nu, that is 1 by 10 power 5, that is equal to 10 power minus 5 seconds. So it will be of the 10 power minus 5 seconds. It will be of the order of 10 power minus 5 seconds. Okay. So the relaxation time will be of the order of 10 power minus 5 seconds. Next. There are 5 curves in figure A. The relaxation for rightmost curve is lambda Ri, and for the leftmost curve is lambda Le. The ratio of lambda Le by lambda Ri will be closest to, will it be closest to 10 power minus 4, or will it be closest to 5, or will it be closest to 10 power 4, or will it be closest to 0.2? To which will it be closer to? So this is what is the curve. You have epsilon double prime by log of nu. So your rightmost curve, again here it is at the frequency of log nu of 5. So your nu is 10 power 5 hertz. That is nothing but 10 power 5 second inverse. So your time is 1 by nu. It has an inverse relationship with frequency. So it is 1 by 10 power 5, that is equal to 10 power minus 5 seconds for the rightmost curve. So relaxation time will be of the order of 10 power minus 5 seconds. So lambda Ri will be 10 power minus 5 seconds. So similarly, your leftmost curve, it is your leftmost curve, as you look at my pointer, it is at nu, log nu of 1. So that means it is at nu of 10 power 1. So it is at a frequency of 10 power 1 hertz. That means your relaxation time for the leftmost curve will be inverse of 10 power 1. That is nothing but 10 power minus 1 seconds. So now they have asked what will be the ratio of leftmost curve relaxation time to the rightmost curve relaxation time. So lambda Le by lambda Ri, that is equal to 10 power minus 1 by 10 power minus 5. So that is equal to 10 power 4. So it will be of the order of 10 power 4. The ratio of the relaxation time of leftmost curve to the rightmost curve will be closest to 10 power 4. Okay, so that's it with the session. Thank you all.